Hello and welcome to Intermediate Algebra, Unit 8, Lesson 2, where we will deal with rational exponents, which simply means exponents that are fractions. So our lesson objective is for you to be able to use and understand rational exponents and understand how they relate to radicals. So what do we mean by a rational exponent? Well, in math, rational has the root word ratio, which really means a fraction in practical experience. So basically exponents that are fractions. And integers are actually rational numbers, so you've already been doing rational exponents, only they've always been in the form of an integer. A rational number is any number that can be written as a fraction. So the number 3 is an integer, but it can be written as 3 with a numerator of 1, and that makes it a fraction, so it is a rational number. But now we're going to start looking at denominators that are different than 1, like 1/2 or 5/3. So if an exponent has a denominator that's different than 1, it can be written as a radical. The denominator of the exponent, in this case the 2 or the 3 here, becomes the index of the radical. So an exponent that has a 2 on the bottom basically involves a square root at some point. A 3 on the bottom means it's involving a cube root at some point. The numerator becomes an exponent on the radical. So for 5/3 as an exponent, you take the cube root of what's inside or what the exponent is touching, and then you raise it to the 5th power. So the other thing that's helpful to observe here is that our rules of exponents, 3 to the 1/2 squared, when I raise an exponent to another exponent, then I multiply the exponents. 1/2 times 2 is 1. So 3 to the 1/2 squared is simply 3. And it's also true that the square root of 3 squared is 3. So 3 to the 1/2 power is equivalent to the square root of 3. Now sometimes in your calculator you're looking for like the 5th root of a number, and there was probably a menu in there that allows you to change the index of the radical, but you could do the number in parentheses, well, the number raised to the 1/5 power. Just be careful, you might need to put the 1/5 in parentheses for proper order of operations. So in more general notation, the definition of a to the 1 over n, notice we're only dealing with numerators of 1 in our exponents right now, means the nth root of a, where n is greater than or equal to a square root, a cube root, a 4th root, etc. So this number on the bottom becomes the index of our radical. So raising something to the 1 over a number just is asking you for that, if n is the number, the nth root of that number. So you see here that if you have a negative exponent, we remember that negative exponents mean if you want to make them positive, you change their position in the fraction. So this goes to, it was on top of an understood 1, but now it goes to the bottom as an a to the positive 1 over n. So now you get 1 over the nth root of a. A can't be 0 in this case because you can't divide by 0. So here are some more concrete examples. The cube root of 4 can be written as 4 to the 1/3. X to the 1/2 is the square root of x. Now notice we don't usually write the 2. You could, it wouldn't be wrong, but that 2 is understood and it comes from the denominator of that exponent. And then y to the 1/5 is the same as the 5th root of y. So now that we have calculators, everybody jumps to use them, but you really don't need them. Some of these are quite simple if you understand what a fraction in the exponent means. And if you are using your calculator, you have to be careful to put the fraction, use the exponent sign and then put that fraction in parentheses if you're using a scientific calculator. Some of the graphing calculators will keep you visually in an exponent, and that's not too hard to mess up, but a lot of people mess it up. But really think about, what is 64 to the 1/2 asking me? It's asking me for the square root of 64. That's just 8. 125 to the 1/3 wants the cube root of 125, which is just 5. Now, negative 16 to the 1/4, some of you are thinking, well, I can't take an even radical of a negative number, but you're not. The exponent only touches the number. You would need the negative 16 to be in parentheses for the 1/4 to apply to the negative. So you do this in the order it happens. There's no grouping symbol, so then you look at exponents. Oh, the exponent 1/4 touches the 16, so I do 16 to the 1/4, which just gives me 4. But this was not done properly in this example because, I'm sorry I didn't type that out, I copied it from somewhere, I should have looked. This should actually be 16 to the 1/4 is 4, I'm sorry, is 2, and then you put the negative sign. The person that did this problem, which I should have caught, assumed the negative 16 was in parentheses, and that so this would not exist. If the negative 16 here is in parentheses, there's no real number solution. But it isn't. 16 to the 1/4 is 2, then you put the negative. This should be a negative 2 for part C. And then there's negative 27 to the 1/3, and you say, uh-oh, the negative is grouped. It's okay because 3 is an odd number. I can get a negative answer for an odd root. And the cube root of negative 27 is negative 3 because negative 3 times negative 3 will give you positive 9, and then times negative 3 once more gives you negative 27. And 64 to the negative 1/3, I change it to the fraction so the exponents are positive. It's easier to manage that way. Now I'm looking for 1 over the cube root of 64. The cube root of 64 is 4, so the answer is 1/4. So we're going to try simplifying these. I want you to stop the video and try these. They're very much in a similar format to the ones we just did. And when you come back, we'll look at the answers. Okay, you're back. Hopefully that you got some progress made on those. So 25 to the 1/2 in part A is the square root of 25, which is 5. 8 to the 1/3 is the cube root of 8, which is 2. Negative 81 to the 1/4, I did the same thing, only this time I did type it. That answer should not be no real solution. I did this problem as if there were parentheses there. So what I should have done is 81 to the 1/4. Well, let's see, the 4th root of 81. If I take the number 3 and raise it to the 4th power, I get 81. So this answer to part C should actually be negative 81. If the question had the negative 81 in parentheses, then raised to the 1/4, the way I've written it would be correct. Sorry about that. Negative 8 to the 1/3, this time it is in parentheses, but it's okay because it's cube root. So I have no idea. I skipped D. So D, negative 8, the cube root of negative 8, that should be negative 2. And this one here should be E, 27 to the negative 1/3. It looks like I did this one correctly. What a surprise. 1 over 27 to the 1/3, 1 over the cube root of 27 equals 1/3. I apologize for those mistakes. At least I have explained them, though. All right, so what about when we have larger numerators, something bigger than 1? It'll still be an integer because a rational number is a ratio of 2 integers. So what if m is 2, 3, or 4? How does this pattern apply? Well, if the nth root of a is a real number, in other words, if a is negative, n is odd, or n is even, a is positive, if that exists, then we can take this m over n exponent and rewrite as the nth root of a, all done. So you take the nth root of a first, then raise it to the m, which is equivalent to raising a to the m and then taking the nth root. And the same rules apply for the negative exponent case. A to the negative m over n is 1 divided by a to the m over n, and then you do just what you did over here. So some examples should be helpful to that. Hopefully these are more correct examples. 27 to the 2/3. So students get mixed up here because they're not sure where the 3 goes, where the 2 goes. The number on the bottom is the new thing. That's the thing we're not used to seeing for many years. So that's the index. That denominator that's not 1 is what causes this to look a little strange. But that gives us the index of the radical. So the bottom becomes the index of the radical. And then the top is what you do to the answer to that radical. So the cube root of 27 squared, the cube root of 27 is 3. 3 squared is 9. 9 to the 3 halves. That means there's a 2 in the index, and that's the case where we don't write it. If there's a missing index, it's understood to be a 2. So you're being asked for the square root of 9, and then being asked to cube that. So that's 3 cubed, which is 27. Now we have a negative exponent, so the first thing I do is change the form so all my exponents are positive. I rewrite 81 to the negative 3/4 as 1 over 81 to the positive 3/4. So 81, so I take the fourth root of 81 first, because that, oh, sorry, I went ahead. So that this 4 on the bottom means I'm going to take the fourth root of 81. That gives me this 3. The 3 on the top means I'm going to cube that. So I get 1 over 3 cubed, which is 1 over 27. So do these a step at a time to avoid mistakes. Now, if you do this in your calculator, 81 raised to the, put in parentheses, negative 3/4, you won't get 1 over 27 unless you change your answer to a fraction. So be aware it's not always just easier to reach for the calculator. All right, so here's a couple I want you to try. The answers are on the next slide. Stop the video, and when you come back, we'll look at the answers. Okay, you're back. Here we go. So 27 to the 4/3 gives you the cube root of 27. The 3 from the denominator goes in the index, raised to the 4th. So you do the cube root first, you get the cube root of 27 is 3. 3 raised to the 4th is 81. 4 to the 3 halves, you're going to take the square root of 4 and then cube it. So the denominator becomes your index, the numerator becomes the exponent you put on the radical. So I get 2 cubed, which is 8. 32 to the negative 2/5 becomes 1 over 32 to the positive 2/5, which is 1 over the 5th root of 32. Then you square that. 1/5 root of 32 is 2. So I get 1 over 2 squared, or 1/4. Hopefully you are seeing the pattern now and it's becoming more recognizable and a little easier to deal with. So just like with exponents that were integers, we have properties for exponents, and the properties are all the same. So that's not a trick. It's not like, oh, I'm going to learn these new things for when it's a fraction. No, if you have an exponent, the rules for exponents apply. So in these cases, I have a 5. I'm going to simplify this, which means basically write it as one term in this case. So when I did that when the exponents were integers, I multiplied the numbers together. So I got 5 times 7. And then x to the 1/2 times x to the 3/4. The bases are the same, so I have to add the exponents. The only thing new here is you don't like to add exponents. I mean, you don't like to add fractions. Either you learn how to do that in your calculator fluently, or remember common denominator is 1/2. Will have to be written as fourths, so I get 2/4. 2/4 plus 3/4 is 5/4. So the rule is the same. Like bases raised to a power, x to the 1/2 times x to the 3/4, you add the exponents and keep the base. For division, our rule was if the bases are like, you keep the base and you subtract the exponents. So deal with the numbers first, reduce the 32 over 16, and it turns out you get a 2. And then when you do x to the 5/3 divided by x to the 3/4, you do 5/3 minus 3/4. And these would both have to be written as 12ths, so you'd get 20 12ths minus 9 12ths, which is 11 12ths. If adding or subtracting the fractions is your issue, I can get you some practice with that and make sure you understand how you could do that more easily on your calculator. Alright, so I want you to try these. They're similar to what we just did. After you've tried them, come back and we'll take a look at the answers. Alright, you're back, so let's take a look. For part A, we do 2 times 5 is 10, and then we have to add the exponents. Nicely, there are both over thirds, so I just do 4 plus 8 is 12/3. But remember, when you have a fraction, you got to reduce it to simplest form. 12/3 is just 4, so you get 10x to the 4th. In part B, we have a division problem. 20 divided by 5 is 4. Now, if this had been 20 divided by 15, you would have just reduced it to 4/3. The two examples we've had, they both come out nice integers, but you would still reduce 20 over whatever's on the bottom the way you reduce any fraction. 20 over 5 happens to be 4. And then I have x to a power, so I subtract the exponents. 4 minus 3 halves is 8 halves minus 3 halves, which is 5 halves. So I get 4x to the 5 halves. Hopefully if you didn't get that, you understand where it came from now, or hopefully you got it first try. Okay, so that's the end of this lesson. You just your mission is to become very fluent with going back and forth from fractions and exponents to radical form and understanding how to evaluate them and simplify them. You have homework to do and some other problems. If you have any trouble, email me. Thanks.